Good afternoon, everybody. Please be seated. Welcome to the first afternoon session of PyCon 2017 for today. Our first presentation will be from Amber Brown on implementing parallelism and concurrency from the ground up. Thank you.
Hello, everyone. Having a good day? Having a good PyCon? OK, so today I am here to talk about implementing concurrency and parallelism from the ground up. Now, this is less about what Python module you'll want to import or how you use it, and it's more about how it all actually works underneath, from the level of the CPU and the operating system up to Python. So how the choices they've made to run code concurrently or in parallel in your computer, how that affects you as a developer. The techniques to run software concurrently and in parallel have been around since the 60s on computers as old as the PDP-1. But it was much, much, much longer until such features came to consumer hardware and consumer operating systems, things that could fit on your desk. Both macOS and Windows have had similar paths, but I'm going with Windows for the context, since it's what I have most experience with. It's fortunate that the sequential consumer versions of Windows gradually introduced more and more concurrency features. And it's a really good way of just mapping the path of how these technologies get more advanced and smarter. But me, I am Amber Brown. I'm probably best known for my work on Twisted and related projects. During the day, I work at a company called Jelly Australia on the future of renewable energy and storage. You can find me on Twitter at Hawkeyowl, which I've got at the bottom there, or Hawkowl on GitHub. It's 1983. There was nothing, just a DOS prompt. Now, you know, MS-DOS was a little bit basic, and I'm going to assume that, you know, like MS-DOS, you don't exactly know what concurrency is, so I'll explain the lingo. Now, the most important terms in this talk are concurrency and parallelism, obviously. They are similar to the user, but vastly different in requirements and how they actually work. But to the user, they both achieve running multiple things at the same time. Now, concurrency is where multiple tasks run interleaved, each task running for a small enough time that all tasks have some work done on some level of a human timescale. You never actually run two things at the same time, because that's impossible when you've only got one processor. But it's a good enough illusion. Parallelism is where two tasks actually run, or two or more, run actually at the same time. So this is like when you've got multiple CPUs, you can actually run two things at the same temporal time. But let's look at how programs at the base level run to understand why running them concurrently can possibly be hard. Programs stores an executable format a little more than a sequence of instructions. And the CPU executes them mostly in sequence. As an example, this is some of the instructions that make up Python. This is the disassemble machine code, which you know, is not quite what the computer runs, but is a human-readable representation. Now, every one of these calls relies on the previous one succeeding. You can't run them in a different order. And each instruction kind of relies on the previous instruction to have the correct state. On a higher level in programming languages, the underlying machine code is hidden from us, and that's transformed from a program like this into the machine code that does what the program represents. You can see the usage of two functions here in this QBasic application. There's print, which prints text to the terminal, and end, which finishes execution of the program and returns to the operating system. If we were to run it, we would get this. The print functions in the exact order we program. One will always come before the other, and the end will always come at the end. Nothing in between, in the same order, always. Classical desktop operating systems like MS-DOS only supported one application at once. You type the application name in, hit enter, and the application ran until it finished, allowing nothing else to happen on the machine. This is fine for things like games, like when playing King's Quest. You want to play the game and just the game. This was a sticking point for office computing and more productive use of computers on the desktop. In the business world, you want to run many things at once. Checking to see if you have an email shouldn't involve completely shutting down the word processor you are writing a report in. So let's fast forward to 1983. What is the future? Or 1985, rather. The future, of course, is Windows. Windows is named after a thing it brought to the IBM PC world. These windows are little containers that held an application, so you could display multiple of them at the screen at once, or minimize one and keep it running while you looked at something else. At this time, we didn't actually have multiple CPUs in desktop computers, so using parallelism to run these applications at once was out. We needed concurrency, and that was exactly what Microsoft provided. So how did they do it? Windows 1.0 implemented what is called cooperative multitasking. Each application had to specifically support Windows, using its APIs to cooperate with the rest of the system. This was built on trust. A trust from the application that would be given enough time to run frequently enough to give a good user experience, and Windows would trust the application to not monopolize the runtime. The API Windows implemented looked like this. Windows implemented a message queue, in which an application would periodically ask for a message while running in a loop. GetMessage is the API that was used here. The system call would call into Windows, and Windows then had a chance to see whether it had something that it wanted to give the application, or whether it wanted to pass control to another application. If it wanted to pass control to another application, that thread running that get message would block until that thread that ran it got called get message, and Windows decided to give control back. The application could potentially use another API called peak message, which wouldn't work. This allowed an application doing heavy processing to be notified about events from Windows, such as key presses, while not relinquishing control. This gave absolute control to the application of what should run and whether anything else should run. Not even Windows could wrest control from the application if it wanted to. Unless some form of interrupt called into it, it was completely powerless. The model meant that you explicitly had to write applications for Windows using this event loop, this message loop. Otherwise, it wouldn't work nicely with everything else. If your application didn't yield enough, didn't check for messages often enough, other applications could seem laggy, or things like cursor movement could even be affected. The implementation of this system is relatively simple and possible on low-end hardware, and it doesn't have a lot of overhead, which made it a good choice. One important thing Windows 1.0 had, though, that most versions of MS-DOS didn't, is virtual memory. When running concurrent applications, you want two things. The first is that you want applications to be portable. This means that the application doesn't have to rely on any certain memory segments being free or being placed in a certain region of memory. If multiple applications access fixed points of real memory, then it could mean chaos, with them rewriting over each other and causing one or both to possibly fail. The second is that you don't want one application to be able to mess with the memory of another application by default. Keeping applications separate in memory means that one application being corrupted and having a failure means that it only affects that application. There's also obvious security things for it as well. You don't want untrusted process to be able to read the memory of everything on the machine. Virtual memory is generally implemented by a memory management unit. Now, that comes on CPUs, I think, past the 886, or possibly earlier. The MMU will translate calls for blocks of memory using a page table into sections of real RAM. This means that every application on the system could possibly put something at memory location 0, but it will actually be put somewhere else, with the application none the wiser. This is also useful for older applications that may expect to control all the memory. Virtual memory is invisible to the application, so it doubles as a compatibility shim. So we have multiple applications now. And with virtual memory, they're mostly none the wiser about each other. But the software has to behave and give up control, and, generally act nice. And as we know, software does no such thing. So say it's 1994. What's the future? Windows 95. It's my favorite operating system, because of this. It's 1994. That was pretty cool. Anyway, Windows 95's advertising focused on two things. The first was multitasking, the other was the internet. The internet didn't really do much for Microsoft because it caused problems for about 15 years. But the multitasking was all right. Windows 95 implements preemptive multitasking. This is where the operating system takes control from the application, preempting it, rather than the application giving control back to the operating system, like in Windows 1.0. The operating system gains back control through use of interrupts from a real-time clock. Interrupts are a CPU feature that allow a code routine to be ran according to some trigger. And modern CPUs ship with a real-time clock that can provide that trigger after a certain amount of time. When we schedule the runtime of different threads in the operating system needs to decide how long to let it run before switching control to another. This amount of time, from start to end, is called a time slice, or a quantum in Windows. Changing between threads is expensive, and I'll go into that. But if you don't switch frequently enough, the illusion of concurrency becomes obvious to the user, and applications seem unresponsive. So picking the right time slice length is important. On Windows XP, it's generally 15 to 60 milliseconds long, and I think it was the same on 95. And on Windows Server, they have a fixed 120 millisecond time slice. The length of this time slice has a bottom limit, the tick rate of the OS kernel. This tick is set in the real-time clock, and hands control back to the operating system every so often to update things like the system clock, process internal events, and reduce the running thread's time slice. Operating systems of 95 up until about 2007 would have a server and a desktop kernel with different tick sizes for each. Every tick, which is about 15.5 milliseconds on Windows, 4 milliseconds on desktop versions of Linux, and 10 milliseconds on server versions of Linux, would be when it does this processing. Since Windows tick is 15.6 milliseconds, that determines the minimum time slice it can allocate to 15.6 milliseconds. Linux had configurable tick, and therefore configurable minimum time slices, but the 4 and 10 milliseconds is what came on the Ubuntu kernel before, like 12.04. Overall, the operating system has to be careful about what time slice it allocates to applications that the user may be interacting with. Windows will give the active Windows whole process a higher priority, and therefore larger time slices more often to keep things responsive to the user. But giving a too short time slice to the only thread that needs to do a lot of work, and then causing excessive switching to threads that otherwise don't have to do anything, means that time is wasted and overall throughput goes down, which is bad for servers. So when a thread is either preempted or cooperatively gives up control, what needs to be altered? Software is generally written as if it was the only thing on the machine and it will run forever. To maintain this lie, the operating system has to save a state of the thread before it preempts it and restore it when it runs again. Ideally, a thread will never know whether it has been preempted and it will still run correctly. To do this, the operating system must save the current workings of the thread to memory. The registers, which can be thought of as high-performance memory direct on the CPU, represent the current CPU level state. The virtual memory table representing the rest of the state in RAM, where it is, and the program counter representing what instruction inside the binary you're running it was up to. Now, many of you know about multi-threading. It's when in the same process you create a new thread to do some task without stopping the current thread. Every process, which corresponds to an instance of a run binary, has one or more threads. Each thread is a chain of instructions with its own stack, its own CPU registers, sort of, and the like, but shares its virtual memory pool with the other threads in the process. The process, meanwhile, contains a state about what user is running it, what binary it is running, and the memory it holds as whole. So that's generally the operating system level metadata. Preemptive concurrency creates new problems. Each thread may be preempted at any time, but the thread doesn't know that. What problems can this cause? The largest is race conditions in multi-threaded code. Let us imagine this code being run in a thread. It reads a boolean from memory, then flips it, saves it back, and reads it again. If it is the only thing running with no preemption, we can expect this output. It'll read a false, and it'll write a true. And when it reads it back again, it gets a true. But what if in the same process, we have two instances of this code in two different threads? Thread 1 might get up to the comment, having read a false and written a true, and then be suspended. Thread 2 may then start, read the true, write a false, and run to completion before the first thread gets control. What if thread 1 then resumes? What does it get before exiting? It gets two falses. So it's a relatively simple example of a race condition. So 1995, we've still got one CPU, but now we're running multiple programs on it that might not play nice, and it's all going fine. Virtual memory and preemptive multitasking means that everything kind of just works together, unless someone writes buggy multi-threaded code, but that doesn't affect anything but just that process. Now let's skip forward to 2001. Windows XP was the first consumer operating system where we could start taking advantage of parallelism and pinball. Simultaneous multi-threading, called hyper-threading by Intel, is a way of providing parallelism without having two true cores. It works by duplicating instruction queues, creating two logical processes that your operating system can use. These two logical processors feed into one physical processor, more efficiently filling in gaps where one logical processor may be waiting from data from cache or for RAM and can't process anything at the minute. Or it may optimize it by having instructions that are both the same from each logical core, allowing it to do them in parallel. Later in Windows XP's life, multi-core processors became quite common in consumer computers. This added a new layer of complexity because along with simultaneous multi-threading, true parallelism was possible. One of the major features of parallelism is causing your threaded code to become even more likely to break. Now, at any line of this code, the memory at position 0x0000 can be changed. Even if you have the whole time slice and your thread is not preempted, another thread can modify the memory you are looking at. This increases the likelihood of race conditions, as some previously dangerous code might have slipped through because it always fit inside one time slice. The proper way to implement this would be to wrap the critical section, the parts that require that the data they operate on not be modified, in a lock of some sort. Mutexes are a different name for a lock. They're basically the same. It's after mutual exclusion. Semaphores are a type of mutex. Come in two types. Come in binary and counting. Binary semaphores are sort of like train tracks, where they can be locked or unlocked, which is useful for protecting resources that can't be mutated or accessed by two things at a time, such as memory or a socket. Counting semaphores are when multiple things can access it, but only up to a certain number. You may have a thread pool with a certain number of threads, and you issue tasks to it. Now, if you hit the limit in that thread pool, a counting semaphore could be used to tell it, no, I can't accept any more requests. Please wait. You have to wait to acquire a lock to send something to this thread pool. One of the major problems with locks is that if written incorrectly, they too can be preempted and fall prey to a race condition. Just like the examples of reading a Boolean from memory, a naively written lock can read a false, try and set a true, and not have done it in time for another thread to read the false before it set the true. So giving two or more threads at that point what is meant to be an exclusive lock. The lock needs to be atomic, that is, the read-write operation has to happen instantaneously to all the other threads. Looking before you leap may actually cause problems in this case, because things can happen between the looking and the leaping. Modern CPUs do ship with atomic instructions to assist with building robust locks, though, with one such instruction being called a test and set. When one thread wants a lock, it runs a loop which uses a test and set instruction, testing for false, and it says if it's false, write true and return an error code, return no error code. Now, that happens atomically on the CPU, so there is nothing that can happen in between them. If there is an error condition, for example, if it tries to write it except it's a true, then you just keep looping, waiting for the lock. This can cause problems, though, because if you have 10 threads trying to acquire an exclusive lock in this method, you can have 9 of them just constantly doing work, trying to acquire that lock, without actually doing anything useful. There's no fixed queue either, so it's kind of luck of the scheduler of which one will be ran next after the lock is freed. So there's more fairer ways of doing this, but it's a basic way of doing it. Code that properly uses locks, doesn't share global state, or otherwise doesn't fall prey to multi-threading issues is called thread safe. Code isn't thread safe by default, so it's important to verify that before it's being used in a concurrent environment. Due to the advent of symmetric multiprocessing on consumer hardware, applications are getting more and more thread safe and are being written to take advantage of the extra cores we have at our disposal. Let's move forward. It's the year 2007, the future. Over the next decade, it becomes increasingly hard to make a CPU faster, and we end up with more cores on a die instead. On the server, which may have 2 processor slots, 32 core configurations, each core with multi-threading, can mean your system sees 64 logical processors. This introduces brand new problems, such as cache coherency and worse cache misses. Many CPUs share some level of cache between physical cores, so in a dual core, being moved from CPU 1 to CPU 2 may not cause issues. But if you're on a 64-core system, and you get moved to an entirely different die, or otherwise cores that don't share caches, you now have potentially lost all the benefits of your past cache, that your past caches had, as well as potentially leaving outdated cache behind. If you were to switch back to that core later, the cache would be gone at that point, so there's no point doing it. So it's important that you stay on the same core, or at least on the same caches. So the operating system has to be smart enough to decide when to move a core to a different, to something with a different cache, because it can be a very expensive operation. Windows 8 killed off the CPU tick, instead scheduling it dynamically. This is important for power saving, as even if we had no work to do, it would still do that tick every 15.6 milliseconds. This does have ramifications for time slices though, as 15.6 milliseconds is no longer the smallest a time slice can be. And it makes larger time slices more efficient, as it's not interrupting them every 15 milliseconds to just reduce its time slice. It'll collate all the timers and all the things it needs to do into one tick, maybe less often, which has really good power saving potential. On Linux, the introduction of tickless kernels meant that there was no longer a difference between the server and desktop builds of the kernel. The CPU is not the only thing that can have concurrent access troubles. Lots of tasks don't fit how modern CPUs execute instructions, and perform better on the kind of processors that that GPUs have. This includes things like 3D rendering, video encoding and decoding, machine learning, and similar problems like that. GPUs don't generally have many memory management units on them, and some applications could corrupt the graphics of other programs. But Windows Vista's display drivers provide both memory segmentation for GPU using applications, as well as GPU time slicing to prevent one application from monopolizing. But overall, what does this have to do with Python? We've talked about CPUs and operating systems a lot. It's really easy to write multi-threaded Python code. The problem is, because of concurrency issues inside the interpreter, Python doesn't actually run Python code in multiple threads. The global interpreter lock, or GIL, means that only one thread in the Python process is actually executing Python. This has the benefit of making a lot of concurrency problems just not happen, because things generally, it means that a whole class of concurrency issues kind of go away. But it doesn't shield you from C extensions misbehaving, because they release the global interpreter lock and can run in parallel. So you have to make sure that not only your Python code is potentially thread safe from being called from C extensions, but your C extensions themselves behave correctly. Another option is to avoid threads as much as possible, and instead adopt cooperative multitasking practices. Python asynchronous I/O frameworks such as Async.io, Twisted, Tornado, and others like Trio implement this, as do frameworks in other languages like Ruby's Event Machine and Node.js in general. But since we're only in a single thread, things that block need to not be used. This means no blind calls to sockets or files, and we have to somehow support every connection we might make to the external world without putting it in a thread. The problem of how to handle many connections in one thread is a big one, but not insurmountable. Every modern operating system ships with some method of implementing non-blocking asynchronous I/O. Every Windows program is event-driven at its core with the getMessage API, so I/O completion ports callback-based design fits really well. On Linux and Unix-based operating systems, we have things like select, epoll, and kq to pick from, depending on the kernel. You use these kernel APIs by calling them with lists of socket numbers, and it tells you what you can and can't send or receive on. Or rather, it tells you what you can receive or send on. If you want to, you just try and send as much as possible, and it says, no, you've filled up your buffers, and then you just do it later. This fits well into an event-driven system. It does work and it does scale. It's how a twisted or async I/O application can support thousands of connections at once on a single core, and also how Nginx can drive massive amounts of traffic efficiently. You can spawn up new processes and communicate with them asynchronously as well, allowing you to execute long-running, high-requirements tasks that don't fit an event-driven design. Of course, we are still at the mercy of the operating system thread scheduler. Even if we're not paying the cost of thread switching in our application ourselves by using cooperative multitasking, we still have to play nice with everyone else. Reducing thread contention is important, as if there's less threads competing for runtime, your time slice can be bigger. Also, you'll get runtime more often. If you still do have a lot of threads, but multiple cores, you can use an operating system feature that's generally called affinity, or similar sorts of words. I'm not sure what it's called on Linux, probably affinity as well, to force a process to stay on a particular core. If you can keep your important worker thread on its own CPU core and set its priority high enough, it is sure to get long, uninterrupted time slices and will meaningfully increase the performance of your single-threaded, event-driven application. If you do need threads, and let's face it, some particular APIs need it, you can reduce the memory overhead by altering the stack size. Every thread needs its own working stack, and sometimes that can be set far too high. If you had 100 threads on your system, and each had a megabyte of stack, which I think is one of Python's defaults depending on operating system, that's 100 megabytes of overhead right there. You can configure how big the stack size is for your particular application and tune it to reduce the memory overheads. One other thing to do is avoiding the thundering herd. Now, the thundering herd is what happens when you have multiple threads on a machine wanting one resource. And then they're all trying to acquire it, and then you'll cause a lot of CPU usage. This comes up when you are sharing a port between different threads. So say you have a socket, and you have 6 different threads wanting to accept a connection on that socket. Now what happens is, if you have those 6 threads and a connection comes in, all of them will be waking up and try and access that socket, even though only one will end up getting it. This is called the thundering herd, where one small action will cause a massive amount of usage. Usually, if you start a thread to do some processing, you'll want to get some data back. But communication between threads can be difficult if you don't have something like the GIL to protect you, as you have to manage your own synchronization. You have to make your own logs. If you put this task in another process and communicate over some bidirectional bus, such as Unix socket, pipes, or TCP, then there's no directly shared state involved. This does now effectively make your application a distributed system, with all the problems that has, but task managers and stuff exist to ease the pain. Additionally, if you communicate over some pipe with different portions of your application speaking over it, it's easy to put that into TCP and then move it off the machine if it gets too big. And we all know where that leads. Microservices. Questions? I think I blazed through that.
Thank you very much, Amber. Do we have yes, we have question microphones. If you have questions for Amber, please queue up at the microphone. The organisers have asked me to say that there is a 10-minute gap scheduled between presentations that is not obvious in the schedule. So if you don't have to leave right now in order to get to your next presentation. Are there any questions?
I have a question.
Sure.
So, given that the CPython has the GIL,
Yep.
and lots of people have different opinions about the GIL, would you recommend for certain applications using something like IronPython or Jython because they don't have the GIL?
I mean, because the sort of thing that I like doing, which is the single-threaded approach with event-driven I/O, the GIL doesn't really come into it. GIL or no GIL, it would be equally as fast. So if you're using something like PyPy, which is a just-in-time compiler, that'll improve the performance of your single thread without, while still having a GIL. So if you do have something where you want a lot of Python, IronPython that can be an option, but there's definitely library incompatibilities. And usually spinning up maybe another instance of Python and talking over TCP might be a better option if you have really long time stuff. And then you don't have to worry about the issues of threading, and you can scale a little bit better.
Thank you.
So I'm fairly new to Python. I have a question about the GIL. Is it single per process, or is there one per interpreter? Or is there?
It's one per interpreter, which generally means one per process.
So can you run multiple interpreters in a process on multiple threads?
That's a good question. I'm actually not sure. I think it might be, I think you can run multiple interpreters in one process, potentially. But it's, the global interpreter lock is internal to the Python interpreter. So if you start up multiple interpreters in your process, but I'm not sure if that's a supported thing that you can do. I'm not entirely sure.
The global interpreter lock is process global. So
OK, process global. Cool.
So one per process, you mean?
Yes.
Okay.
So one per process. Cool. Do we have any more questions? How about any statements?
You said that thing about the GIL being limited to one thread. And my understanding is that the Python threading module uses multiple OS threads.
The Python what module, sorry?
Threading?
Yeah, it'll run multiple OS threads, so it doesn't limit you to actually using one thread. It just means that all of those threads can only be executing and interpreting Python. Only one of those threads can be interpreting Python at any time. So those operating system threads, if it's like a C extension, that'll be fine because that releases the GIL. So it's just that if you spawn up multiple threads with Python code, it'll just run like thread 1, thread 2, thread 3 sort of thing. So, anyone else? No statements? Cool. Thank you very much, everybody.
Please thank Amber. Thank you.
Cool. I think I went through that pretty quickly.